Okay, so we'll go back to another video. So here we want to find a nice value for the following infinite sum. So we have the square root of 2 minus 1 quantity to the 2n plus 1 divided by 2n plus 1 quantity square. And so a lot of evaluating this infinite sum within that process is heavily relying on dilogarithm identities. So you pretty much be seeing a lot of that in this video. But if for the beginning of the work, we're actually going to be utilizing some integrals, that way it'll help us rewrite our infinite sum a little bit easier, to the point that once we evaluate it, then that's where the dilogarithm identities come into play. So nothing really much that needs to be put in, since, again, this entire video for the most part, I'd say maybe more than 70% of it is you'll be seeing just dilogarithms and identities and all that stuff. But it does come down to a nice value once we get to reach the end of it. So with that, let's actually just jump right in. So notice that I'm going to call this capital S. So this infinite sum can be written as the following. So we have infinity and then n is equal to 0. So for 1, I have that this is 1 divided by 2n plus 1. And then if we can actually multiply this with the integral, the definite integral from 0 to the square root of 2 subtract 1 of x to the power 2n then dx. So if that actually fixes that up, we're actually pretty much just taking into a backwards approach. So I'll actually just move the summation inside of our integral. So let's see, so we have 0, the square root of 2, and then minus 1. And so what I'm going to do from here is that once this is moving backwards to the infinite sum, so it's basically x to the power 2n divided by 2n plus 1. And what I'll do is I'll multiply and divide an x, such that means that I'll change the exponent to plus 1, and then I can actually put the x outside of our sum, since it doesn't heavily rely on n. So this will be 1 divided by x, and then multiply the infinite sum from n is equal to 0 of x to the power 2n plus 1, and then divided by 2n plus 1, then multiply with dx. And so by definition, this infinite sum is in a nice form of what's known as the Maclaurin series of the inverse hyperbolic tangent. And this is valid such that the absolute value of x is actually less than 1. So we can do that to actually do the following replacement. So I'm actually just write this over here. So 0 to the square root of 2 subtract 1 of the inverse hyperbolic tangent of x, and then divided by x, then dx. So that's nice. And then by definition, we can actually use the identity that, I'll put this on the side, that the inverse hyperbolic tangent of x is written in form of a natural log. So this is going to be the same thing as 1/2 times the ln of 1 plus x divided by 1 minus x. And if we want to, we can actually simplify things even further with the natural log properties to say that this is 1/2 ln of 1 plus x, and then subtract 1/2 times ln of 1 subtract x. Okay, so with this in mind, so now we can actually just replace this for our integral, and then also applying some linearity. So that'll help us to say that s is equal to, so I'll just rewrite the same thing again, 0, the square root of 2 minus 1, the inverse hyperbolic tangent of x divided by x dx is, in other words, the same thing as saying 1/2 times the integral from 0 to the square root of 2 subtract 1 of ln of 1 plus x divided by x dx, and then subtract with 1/2 times the integral from 0 to the square root of 2 minus 1 of ln of 1 minus x divided by x, and then dx. And so now here's a little identity we'll be using, and you can already guess, as I already said in the intro, what we'll be using a lot. So by definition, the dilogarithm, so written as Li order 2 of x, in other words, this can be written as the form of a definite integral from the negative integral from 0 to x of ln of 1 minus u, and then divided by u, then du. So utilizing this, and this is also mentioning that x can be any complex number. And so if I were to, let's say, take the derivative of our dilogarithm function, so that means d dx of our dilogarithm of x, then all I have to do here to differentiate this is just use the fundamental theorem of calculus and say that this is indeed just negative ln of 1 minus x, and then divided by x. Now with this in mind, so we can actually now put this back together. So this is actually just coming for this integral over here that we can actually replace. So therefore, now just to mark an asterisk, 1/2 multiplied by the integral from 0 to square root of 2 minus 1 of ln of 1 minus x divided by x dx. Basically, we're just going backwards. And so in other words, that's the same thing as saying negative 1/2 of the dilogarithm at x. and then we just evaluate it from our bounds to 0, the square root of 2 minus 1, and then 0, we know that the dilogarithm of 0 is just equal to 0, so that's actually nice, and that'll just leave us with negative 1/2 the dilogarithm at the square root of 2 minus 1. Okay, and so another interesting thing, and I'll just put this over here, that if I were to take the derivative of the same dilogarithm, but I said our input's going to be at instead negative x. So in other words, you just do the same thing if applying a little bit of chain rule here and there, and so now that'll just yield us with, this time it's going to be negative ln of 1 plus x and then divided by x. And so now going back to here, we can actually now finally calculate what we need to calculate. So 1/2 the integral from 0 to the square root of 2 minus 1 of ln of 1 plus x and then divided by x dx is indeed just going to equal to negative 1/2 then the dilogarithm evaluated at negative x, evaluate our bounds from the square root of 2 minus 1 and then 0. Again, the dilogarithm of 0 is just 0, so that's nice. And so now that'll just yield us with negative 1/2 and then the dilogarithm. Now just flip the sign, so now this will instead be 1 subtract the square root of 2. So now that everything's in mind, so that means S, therefore, so far that we have calculated to say that is written as the following. This will be 1/2, then the dilogarithm at the square root of 2, subtract 1, and then subtract 1/2, then times the dilogarithm at 1 subtract the square root of 2. So if you want to, you could just leave things at that if we want to, but we're going to take things a little even further, and that's why I mentioned a lot of this stuff comes into play with a lot of the dilogarithm identities. So some first things to say is that you can observe that our integrand, the inverse hyperbolic tangent of x over x, is actually a real number in between our interval from 0 to the square root of 2 minus 1. So therefore, implying that this entire integral is indeed a real number. So this is where the identity of dilogarithms come into play. And to keep this in mind with these identities, they actually have complex numbers involved with it. So to take things a little more of a approach, that we just need to focus on just the real part of our s, aka the integral that we just went through. So complex numbers, so of course we're going to have some imaginary units involved here and there and everywhere, but all we need to do is just focus on just the real part in order to get the following infinite sum that we want to achieve for. So with this, that means I can just set this as, in other words, the real parts. So for one, I'll just factor out the 1/2, and then now we'll just say that as the real. So 1/2, and then multiply with the real part of the dilogarithm evaluated at the square root of 2 minus 1, and then subtract the dilogarithm at 1 minus the square root of 2. Now with this in mind, now let's actually get into the real fun. So let me actually box this to see if this is what we have achieved for so far. So now here comes evaluating the inside of our real part. So I'll say now Li sub 2 is still the dilogarithm of square root of 2 minus 1, then minus the dilogarithm at 1 minus the square root of 2. So you can actually rewrite this in something a little more creative. Now, what you're going to see upcoming ahead, it seems like it's a little pointless and doesn't make sense, but again, the dilogarithm identities will come in handy with this, everything that's in the combination of the sums and differences. So with this in mind, that means I'm going to have the following. So this means what I can rewrite this as is the dilogarithm at the square root of 2 minus 1. Add this with the dilogarithm at the square root of 2 plus 1. Then I can subtract the dilogarithm of the square root of 2 plus 1. Add this with the dilogarithm at negative the square root of 2. Subtract with the dilogarithm at the square root of, or the negative square root of 2. Add this with the dilogarithm at the square root of 2. Subtract the dilogarithm at the square root of 2. And then lastly, subtract with the dilogarithm at 1 minus the square root of 2. So in other words, to put everything together, so that means S is going to equal to just 1/2 times the real of the dilogarithm at the square root of 2 minus 1, subtract, or rather add, everything's in factors, and then we're going to have some minuses later that'll come in handy. The dilogarithm at the square root of 2 plus 1 minus 1/2 times the real of the dilogarithm of the square root of 2 plus 1. Then add this with the dilogarithm at the square root of 2. And then add this with the dilogarithm at this negative square root of 2. And I'm going to add this with the real, 1/2 times the real of the dilogarithm at the negative square root of 2, add this with the dilogarithm at positive square root of 2, and then lastly subtract with 1/2 times the real of the dilogarithm at the square root of 2, add this with the dilogarithm at 1 minus the square root of 2. Okay, so with all this, that's actually we have to calculate. So the steps we're going to approach to this is we're actually going to deal each single argument on its own for the real parts one by one with these utilizing the dilogarithm identities. Then after putting everything together, we can actually combine the sums, take the real part, and so therefore that will actually yield us to the true value of our S, the infinite sum that we want to achieve for. So with this, I'm actually going to get rid of everything here and then move on to calculating with using the dilogarithm properties. Okay, so far to establish S is equal to 1/2 times the real of each of these arguments, so on and so forth, with a 1/2 minus 1/2 plus 1/2 minus 1/2 with the reals. And so these three are actually going to be the nice identities of the dilogarithm function that we'll actually be utilizing to help calculate each of these dilogarithm arguments of the reals. So we're going to start off one by one, calculate each one thing at a time, substitute that back in, take that real part, and then put everything combined together, and then that's our S, that aka the infinite sum that we want to achieve for. So let's start off with the first one, the dilogarithm of the square root of 2 minus 1 plus the dilogarithm of the square root of 2 plus 1. So what we'll be using is that we're actually going to be using this identity, the first one listed z, and then with argument of 1 over z. So therefore, the dilogarithm of the square root of 2 minus 1, and then add this with the dilogarithm of the square root of 2, and then plus 1. So therefore, that means that will yield us negative pi squared divided by 6. And that's nice since, because if we use the correct arguments, it's supposed to be a square root of 2 minus 1. And if I put that under here, that's basically we can just multiply with its conjugate, and we'll actually get this following argument just as we want for this identity. So that will yield us negative pi squared divided by 6, then minus 1/2, then multiply ln square of 1, subtract the square root of 2. Okay, so now to continue forward, we have the ln of a negative number, which is not allowed, but we can actually fix that by using the principal branch. So what I can do here is I have the natural log of 1 minus the square root of 2. I can factor out that negative, so that'll switch the sign to say square root of 2 minus 1, which is indeed a positive number. And so rewriting this, so I have the ln of the square root of 2 minus 1, then multiply with the principal branch to say that negative 1 is equal to e to the power I times pi. And if we just utilize some of the natural log properties, we have that this is the natural log of the square root of 2, subtract 1, add this with ln of e to the I pi, which is just I times pi. And so now just to put everything back in, so equals, just to continue forward from the first line over here, is now negative pi squared divided by 6, then subtract 1/2, then now substitute everything back in, so the natural log of the square root of 2 minus 1, add this with I times pi, and then square that. And so now performing things even further, that if I expand this out and then also simplify some things out, because we also have some common terms that we can actually reduce down to, will yield us with pi squared divided by 3, then subtract 1/2 times ln square of the square root of 2, subtract 1, and then minus I times pi times the natural log of the square root of 2 minus 1. And so therefore, if I just take the real parts, so the real of our first line, the dilogarithm of the square root of 2 minus 1, add this with the dilogarithm of the square root of 2 plus 1, then that means this is actually just taking the real part, therefore that's just equal to pi squared divided by 3 minus 1/2 times the natural log, 1/2 times the natural log square of square root of 2, subtract 1. So now that's done. So let me actually take things one step at a time, and we'll actually fill in the gaps and say that S is equal to 1/2, and then fill in this gap over here. Moving on, so now let's actually calculate this argument over here, the dilogarithm of square root of 2 plus 1 plus the dilogarithm of the negative square root of 2. So what we'll be using is that we're actually going to be using this argument over here, because if I actually just plug in the identity correct, the square root of 2 plus 1, and then if I actually put this back in and substitute that in, we get exactly what it is that we want to use for that identity. Putting things forward, so that means now the asterisk, then I have that the dilogarithm of the square root of 2 plus 1, and then add this with the dilogarithm of negative square root of 2. Using this identity over here is going to give us pi squared divided by 6, then subtract the natural log of the square root of 2 plus 1 multiplied with the natural log of the negative square root of 2. So of course you can't have a negative number. And so another thing to simplify even forward, that I can actually just multiply I can actually just fix this up such that this is a negative, so that becomes 1 divided by this input over here. Fix it with the conjugate, multiply with its conjugate, and so therefore instead out and just change this to a plus, so pi squared divided by 6 plus the natural log of, now this will be the square root of 2 subtract 1 and then times ln of the negative square root of 2. And so, of course, doing the same thing just like before, we can't have a negative argument. We can change that up using the principal branch. So put this forward, ln of negative square root of 2. In other words, that's the same thing as natural log times the square root of 2 multiplied with the principal branch. Negative 1 is equal to e to the power I times pi. Then putting things even forward, then we have that this is just ln of the square root of 2, and then add this with I times pi. And so we'll just substitute everything back in. So equals, continuing on from this line over here, this will yield us pi squared divided by 6. Then add this with the natural log of the square root of 2 minus 1 multiply with ln of square root of 2. And then add this with I times pi multiply with ln of the square root of 2 subtract 1. And so now all that's left is just take the real part. So therefore the real of the dilogarithm of the square root of 2 minus 1, then add this with the dilogarithm of negative square root of 2, and so therefore just equate the real parts. So that means it's just pi squared divided by 6, then add this with the natural log of the square root of 2 minus 1 multiplied with ln of the square root of 2. And just like that, now we can actually just put this back in, continue moving forward, so minus 1/2, and then just substitute our value back into here. Okay, so now we got our two values over here that I'll just underline just so you don't get confused on what's what. These two over here, we just plug them back in. So now getting rid of this, we're gonna move on to calculate these last two arguments over here and then continue forward with combining everything together to get our final value for s. All right, so now the next one we're going to do is the dilogarithm of the negative square root of 2. Add this with the dilogarithm of the square root of 2. The identity we'll be using is this following over here. Very easy enough to say that I just replace this with the square root of 2, put this back in. This is exactly what we want. So now let's actually get into that. So therefore, saying that the dilogarithm of negative square root of 2, add this with the dilogarithm of the positive square root of 2 is indeed just equal to 1/2 times the dilogarithm of square root of 2 squared, which is just number 2. This looks like we can't do much, but we're actually going to take things into a little creative approach that at first it might seem a little useless, but actually if we take that information and plug this back in, we will get what we want to achieve for. So using this identity, the z and then 1 minus z over here, and then plugging in for the value of z is equal to 2, so that means now the dilogarithm of 2, and then add this with the dilogarithm, so put this as, now that's going to be negative 1, is going to yield us pi squared divided by 6, then minus ln of 2, and then multiply with ln of negative 1. So of course, same thing as you have the negative ln of 1, which you can't have. But first, let's actually write a little bit of some functions that we'll be using, so in terms of definition. So definition of our first function we'll be using is that the dilogarithm is represented in the following infinite sum series. So this is the infinite sum at n is equal 1 of x to the power n divided by n squared. So what I have to mean that the dilogarithm of negative 1 is, in other words, the same thing as that, just plug the negative 1 for our input, n is equal 1 of negative 1 to the power n and then divided by n squared. We can fix this up a little further such that I can multiply and divide a negative 1, so that'll change the exponent, but that also make this infinite sum negative. So infinite sum n is equal 1 of negative 1 to the power n plus 1 and then divided by n squared. And also another function we'll be using in definition is the eta function. So eta of s is equal to the infinite sum at starting with n is equal to 1 of negative 1 to the power n plus 1 and then divided by n to the power s. As you can see, we have that s is equal to 2 and there's a negative, so therefore this is the dilogarithm of negative 1 is the same thing as the negative eta of 2. Okay, so from here, And then now to continue forward, we'll be actually using another equation, a functional equation that actually relates with the Riemann zeta function that says that eta of s is equal to 1 subtract 2 to the power 1 minus s multiplied by the Riemann zeta of s, the zeta function. And so if I just plug in 2 for our eta function, so eta of 2 is just equal to 2 plugging back here, so 1 minus 2 to the power negative 1, so it's just 1/2, so 1/2 multiplied by Riemann zeta of 2, that's just Basel's problem, so aka pi squared divided by 6, 1/2 times pi squared divided by 6 is equal to just pi squared divided by 12, which is the eta of 2, then the negative, so therefore this is just equal to negative pi squared divided by 12. Okay, so now that that's done, we have our dilogarithm at -1, and then now just going back to finishing this left-hand side, so again, I can actually just supply the principal branch, and then so therefore I'll get that negative ln of -1 is the same thing as I times pi. And if I just put this back in, so that means now so far we have the equation, the dilogarithm of 2, and then subtract pi squared divided by 12 is equal to just pi squared divided by 6 minus I times pi and then times ln of 2. And so therefore that if I want the Riemann zeta 2 on its own, so I'll just add the pi squared divided by 12 on both sides, simply that'll just yield us with pi squared divided by 4 and then subtract I times pi and then ln of 2. Therefore, if I just go back to over here, that means we have found that the dilogarithm of 2 is equal to this value, just replace this back in. And so therefore, going another step further, that the real part of the dilogarithm of negative square root of 2, add this with the dilogarithm of the positive square root of 2, is in other words, just the real part of 1/2 times the dilogarithm of 2. So I just multiply 1/2 to this entire thing and we take the real part, therefore it's just equal to pi squared divided by 8. All right, so there we have it. We have calculated our third argument of this entire S. So now I can actually just plug this back into over here. Okay, so now with everything in mind over here, so now I'm just gonna get rid of this and now we're gonna calculate the final argument we need to evaluate for. So last is left is the square root of 2, add this with 1 minus the square root of 2. So last identity we'll be using is this one, the dilogarithm of z plus dilogarithm of 1 minus z is equal to the right-hand side. So if you notice that if you actually plug the inputs correctly, we'll get exactly just as this form over here and just plug in the right necessary argument that we need to achieve for. So now the dilogarithm of the square root of 2, add this with the dilogarithm of 1 subtract the square root of 2. In other words, is pi squared divided by 6, subtract the natural log of the square root of 2, then times ln of 1 minus the square root of 2. So now we just have to focus on this again. Yet again, that's a negative number, so you can't have a negative number within the natural log. So applying principal branch again, so I'll just factor out the -1 of our input. So that'll give us the natural log of the square root of 2 minus 1, and then multiply, so e to the power I times pi. And so applying natural law properties, that'll yield us ln of the square root of 2 minus 1, and then add this with I times pi. So now putting things back together, so equals going to the continuation of this line over here is going to yield us pi squared divided by 6, subtract the natural log of the square root of 2, times the natural log of the square root of 2, subtract 1, and then subtract I times pi, then multiply with ln times the square root of 2. And so lastly, all you have to do is just take the real part. So therefore, going here, the real of the natural or the dilogarithm of the square root of 2, add this with the dilogarithm of 1 subtract the square root of 2, it's just indeed equal to just pi squared divided by 6 minus ln of the square root of 2, then multiply with ln the square root of 2 subtract 1. Okay, so we've actually calculated all 4 of the arguments, so let me first put this back into over here, and then we can continue forward and simplifying everything out to get S. Okay, so now that everything's put in together, so this is our final step, just simplifying everything out. So we have 1/2 times our answer from here, minus 1/2 times our answer from here, from the real part, plus 1/2 times our answer, which is here, and then minus 1/2 times the answer of the real is over here. So lastly, all we have to do, simplify, I reset that again. So now if we put everything back together, so that means over here, I'll have pi squared divided by 6, then minus 1/4 times the natural log square of the square root of 2 minus 1. Okay, then moving on, so over here, so now I have pi squared divided by 12, then subtract 1/2 times the natural log of the square root of 2 minus 1, then multiply with the natural log of the square root of 2. Moving on, then multiply 1/2 to pi squared divided by 8, aka plus pi squared divided by 16. Then multiply the negative 1/2 into over here, so that means minus pi squared divided by 12. Then add this with the natural log, or rather 1/2 times the natural log of the square root of 2, and then multiply with the natural log of the square root of 2, subtract 1. As you see, we're going to actually have some stuff that cancel out. One thing you'll notice is that this is going to cancel out, and so is this. And so now what's left is we have pi squared divided by 6, then over here minus 1 over 4 and an L of this, minus pi squared divided by 12, plus pi squared divided by 16, minus pi squared divided by 12. Okay, and so now we just combine everything together. So all that's left is that these 4 of the associated with the pi squares are left to be combined together. And so if you do all this, this will yield us pi squared divided by 16. And then all that's left is minus 1 over 4 times the natural log square of the square root of 2 minus 1. And so therefore that is our final answer for S. S aka being our infinite sum that we want to calculate this entire time. So that was a lot of talking. I'm already short of breath, but it actually does come down to a final answer, a nice final answer as mentioned. So there we have it. All that dilogarithm identities used with a simple integrals here and there for the beginning portion, but it all comes down to this just like that. So there you have it. So that's pretty cool if you ask me.